Welcome to space science. Most earthquakes arrive with force. This one does not. It begins in silence, deep beneath the earth, hidden from human senses and revealed only through instruments, patterns, and patient scientific observation. Along a quiet coastline, nothing seems unusual. The sea moves as it always does. The land appears still, yet far below, a rare earthquake is slowly unfolding, and its signals are serious enough to make scientists sound the alarm. In this documentary, space science follows the hidden motion, the science behind it, and why this quiet event has captured global attention. If this kind of deep Earth mystery is worth exploring, please like the video, subscribe to Space Science, and share it with someone who loves science. Along one edge of the world, the surface appears quiet enough to escape notice. The sea rises and falls in its usual rhythm. A coastline carries on under wind, cloud, and shifting light. Wet sand darkens, then dries. Small harbours receive boats. Roads cross low ground and climb toward older rock. Forests and grasslands stand over slopes that have been shaped by long weathering, rain, and gravity. On most days, nothing in this broad view suggests that stress is gathering far below. The ground seems firm, the horizon seems settled, yet the visible surface of Earth is only a thin outer skin, and from time to time that skin records a change before the cause is fully understood. In places where rare earthquakes occur, the first signs are often not dramatic. They do not always begin with falling masonry or sharp jolts felt in a sudden instant. Instead, the surface may change in ways that are slow, sparse, and easy to miss. A shoreline may rise by a small amount or sink by a small amount. Tidal flats may hold water a little longer than before, or drain a little sooner. Marsh plants may stand in ground that has turned slightly saltier or slightly drier in some places. Piers and markers that once matched the tide in a familiar way begin to sit at a subtly different height. The change can be so small that no single step, wall, or tree can make it obvious. It becomes visible only when one careful record is placed against another. On land, the first evidence may come through repeated surveying, through reference points fixed to bedrock, or through satellite views that compare the position of the ground across time. A hill slope that seems unchanged to the eye can shift by a fraction of a hand's width across many days. A broad coastal plain can tilt so gently that rivers continue to flow as before, while instruments later reveal that one side has lifted and the other has settled. These changes are not the movement of loose soil after rain, and not the sagging of structures under their own weight. They reflect motion within the crust, the outer rocky shell of the planet, where stress accumulates as great blocks of earth press, drag, and resist one another. The places that bring scientific alarm are often those where the landscape already carries the marks of older strain. Long mountain belts stand inland from deep ocean margins. Island arcs curve across water where one plate descends beneath another. Some coasts rise in steps over long spans of time, leaving old marine terraces stranded above the present sea. Elsewhere, drowned valleys show that the balance between land and sea has shifted again and again. In these regions, the surface is a patient archive. Cliffs, river mouths, uplifted shell beds, and layers of mud all preserve evidence that the ground does not remain still over geological time. A rare earthquake enters this archive as a new and delicate line. What makes the first surface signs so important is their pattern. A single cracked path may mean little. A small landslide may follow an ordinary storm. A damaged retaining wall may reflect poor construction. Scientists look instead for coordinated change over a wide area. They study whether the land has moved toward the sea, whether part of a coast has dropped, whether another part has lifted, and whether the motion forms a shape that matches known tectonic structures. Tectonic refers to the slow movement and interaction of Earth's outer plates. When the pattern is coherent, the quiet surface begins to speak clearly. The sea can also reveal early signs. In some rare events, pressure changes along the seafloor alter the height of the water column by a very small amount. Tide gauges may record a shift that cannot be explained by weather alone. Coastal currents may respond to a changed seafloor shape, though this effect is usually subtle. In the deepest settings, instruments anchored offshore can detect pressure differences that suggest the seabed has moved. None of this resembles the towering wall of water that belongs to the public image of a major tsunami. These signals are measured, not witnessed in fear from shore. They belong to the realm of careful comparison and patient monitoring. At the human scale, the surface often remains ordinary while the scientific meaning grows more serious. People walk across the same streets, fishing vessels leave at dawn, rain falls on roofs, yet within research centres and monitoring agencies, attention gathers around maps, time series, and repeating observations. A coastal station that has drifted seaward by a small but persistent amount becomes more than a dot on a screen. A string of stations doing the same thing becomes a physical statement about the crust below. Alarm, in this context, does not mean panic. It means that an unusual process may be underway in a place where the stakes are high. Rare earthquakes often differ from common earthquakes in the way they express themselves at the surface. Ordinary earthquakes are usually known first through shaking. People feel them, objects rattle, and seismic waves arrive quickly enough to define a sudden beginning. Rare events can unfold more slowly. Their surface expression may appear through displacement before it appears through sensation. The land shifts, but many people notice nothing at all. This difference matters because it can delay recognition outside the scientific community. It also matters because slow or unusual fault motion can change stresses in nearby regions without announcing itself in the familiar way. The broad environment around such an event helps shape what is seen. Along some coasts, soft sediments absorb and disguise motion. In other places, hard rock preserves clean measurements from anchored instruments. Dense vegetation can hide fresh ground cracks. Tidal wetlands can magnify small changes in elevation because plants and water respond quickly to slight differences in flooding. River deltas can complicate the picture because they subside naturally over time. For this reason, the surface is never read in isolation. Every measurement must be placed in its local setting, and every local setting must be compared against the regional pattern. Even when the first signs are clear, uncertainty remains. Observations may indicate that the ground is moving in an unusual way. They may show that a broad section of crust has begun to deform. It may remain uncertain at first whether the process is a rare slow earthquake, a related form of slip, or a combination of several movements acting together. Scientists do not begin with certainty. They begin with repeated evidence, careful separation of signal from noise, and the knowledge that Earth often hides its causes beneath ordinary appearances. So the opening scene is not one of chaos but of attention. The rare earthquake announces itself first through the quiet world above it. A coast lifts by a little, another settles by a little. The shape of the land changes just enough for instruments and repeated records to detect it. The surface remains calm, yet beneath that calm lies a message from the deeper structure of the planet. The message is faint, broad, and measured in patience. It is the first sign that something uncommon is moving within the earth, and that the stillness of the landscape is only the outward face of a much larger strain. Across the same region, the landscape remains outwardly calm, but the effort to understand it becomes more exact. Rare earthquakes are often first recognized not by a single witness, but by a network. That network extends across hills, valleys, ports, islands, and the open sea floor. It includes instruments fixed to bedrock, receivers that listen to satellites, pressure sensors anchored in deep water, and long records of motion stored in quiet computers. Each instrument observes only one narrow part of the world. Together they form a listening system spread over land and sea, able to detect changes too small and too slow for ordinary senses. The most familiar of these instruments is the seismometer. A seismometer is a device that records motion of the ground. In an ordinary earthquake, it captures the arrival of seismic waves, the vibrations that travel through Earth after a sudden rupture. The record from such an event often shows a sharp beginning, a strong pulse, and a sequence of waves moving at different speeds through crust and mantle. In a rare earthquake, the pattern may be very different. Some rare events produce signals so weak and spread out in time that they do not resemble the sudden trace of a typical quake. The line on the record may show faint energy, scattered tremor, or sometimes almost nothing that can be recognized without careful analysis. This weak signal is part of the challenge. A rare earthquake can move a fault significantly while radiating only limited seismic energy. That means the fault may slip, yet the usual strong shaking does not appear. Standard earthquake catalogues, which are built around the detection of sharp seismic arrivals, may not capture the event fully at first. Scientists therefore rely on more than one observing method. They combine seismic records with geodetic records. Geodetic means the careful measurement of Earth's shape and the position of points on its surface. This approach turns the crust into a measured surface, not just a stage for shaking. One of the most important tools in this work is the Global Navigation Satellite System receiver, often discussed through the use of GPS. Fixed stations on land receive signals from satellites and calculate their positions again and again with great precision. A station bolted to solid rock may appear motionless in daily life, yet over time it reveals a steady tectonic drift. In an active region, that drift can change. A station may begin to move seaward a little faster, or upward by a small amount, or sideways in a direction that differs from its usual long-term path. When many stations show coordinated motion across a broad area, the pattern can reveal that strain is being released on a fault beneath them. This kind of measurement is especially important for slow earthquakes, which may unfold over days, weeks, or even longer. The ground does not leap all at once, it creeps. A single day's movement may be slight enough to vanish into noise from weather, temperature, or instrument limits. But when the same tendency continues and is confirmed at station after station, it becomes a coherent physical event. Scientists then compare those changes against models of fault slip. From the pattern at the surface, they estimate where the fault is moving, how much it is moving, and over what area the motion is spread. Satellites offer another view. Radar satellites can compare repeated passes over the same region and detect changes in surface position through a method called interferometry. In simple terms, the method compares the phase of reflected radar waves from one pass to another. Tiny differences can show whether the ground has moved toward or away from the satellite. The result is not a photograph of the earthquake itself, but a map of surface displacement. In ideal conditions, these maps reveal broad, quiet warping of the land. They are powerful because they cover large areas rather than isolated points. They are limited because vegetation, water, snow, and atmospheric effects can blur the signal. Even so, when radar maps and satellite position records agree, confidence grows that the observed deformation is real. Offshore, the problem becomes harder. Many rare earthquakes occur along subduction zones, where one tectonic plate descends beneath another and much of the crucial motion lies under the sea. The ocean hides the ground that matters most. There are fewer permanent instruments there. Access is difficult, and measurements must survive pressure, corrosion, and long isolation. Yet offshore observation is essential. Pressure sensors placed on the seafloor can detect slight changes in the height of the water above them. If the seabed rises or sinks even by a small amount, the pressure record can reveal it. Ocean bottom seismometers can also record local tremor and weak seismic activity close to the source, where land stations may hear only a dim version of the same event. In some regions, fiber optic cables have begun to add another layer of observation. These cables, already stretched across the seafloor for communication, can sometimes be used as long sensors for vibration and strain. The technique remains more developed in some settings than others, and it does not replace established systems, but it shows how the observing network continues to expand. Rare earthquakes demand such expansion, because they often hide between the strengths of older methods. One instrument alone may miss them. A combined network can begin to reveal their form. Time is as important as space in these observations. A common earthquake declares itself in seconds. A rare one may emerge only when scientists compare records across days or weeks. Monitoring centers therefore study both immediate signals and slow trends. They watch daily solutions from satellite stations. They filter seismic noise to isolate tremor, a weak and often prolonged vibration linked in some places to slow fault motion. They compare pressure records offshore. They test whether the apparent signal persists after tides, storms, temperature changes, and instrument drift are taken into account. The work is quiet and methodical. Alarm begins not from one dramatic trace, but from many separate records that lean in the same direction. This process also depends on reference frames and long histories. To know that the ground is changing unusually, scientists must first know how it behaves normally. Years of previous measurements define the background rate of tectonic motion. Seasonal effects must be understood. Coastal stations may shift slightly with groundwater changes or surface loading from rain. Temperature can affect hardware. Even the atmosphere can delay satellite signals and distort radar views. The observing network does not merely collect data. It learns the character of each site so that true deformation can be separated from the ordinary motion of a living surface environment. In the case of a rare earthquake, this separation becomes the center of early interpretation. Observations may show a broad displacement field that fits slow slip on part of a plate boundary. Seismic data may reveal faint tremor, but not the impulsive waves expected from a normal rupture. Offshore sensors may register subtle changes consistent with seabed motion. None of these pieces is sufficient alone. Together they begin to support a physical explanation. The event becomes visible not as a loud shock, but as a convergence of quiet evidence. That is why scientists listen through networks rather than moments. The instruments do not grow tired, and they are not distracted by the calm appearance of the day. They record motion continuously. They preserve the difference between what seems still and what is slowly changing. When a rare earthquake begins, the first true witnesses are these dispersed devices across land and sea. Their records gather into a pattern, and that pattern gives the event its first clear outline. In that outline, concern begins to take shape, not from fear, but from the recognition that an uncommon movement is underway beneath a region where ordinary shaking is not the whole story. Beyond the local stations and the individual coastlines lies the broader setting that gives the rare earthquake its place in the structure of the planet. The event does not occur in isolation. It belongs to a regional system shaped over millions of years by the motion of tectonic plates, the slow creation and destruction of crust, and the steady transfer of stress across boundaries that stretch for hundreds or thousands of kilometers at the surface. This setting may appear as a chain of islands, a long offshore trench, a line of coastal mountains, or a continental margin that drops into deep ocean. Beneath those visible forms lies a moving architecture of plates that defines where strain gathers and how it may be released. Earth's outer shell is divided into large rigid sections called tectonic plates. These plates move slowly over the deeper, hotter part of the planet. The rates are small in human terms, often only a few centimeters in a year, yet across geological time they are enough to open oceans, close basins, raise mountain belts, and recycle crust into the interior. Where two plates meet, the boundary takes different forms. Some boundaries pull apart, some slide sideways, some converge, meaning that they move toward one another. Rare earthquakes that draw strong scientific concern often occur in convergent settings, especially where an oceanic plate descends beneath another plate in a process called subduction. Subduction zones are among the most active and complex regions on Earth. They commonly produce deep ocean trenches, volcanic arcs, and some of the largest earthquakes known. The descending plate bends downward and enters the mantle beneath the overriding plate. Sediments carried on the ocean floor may be scraped off and added to the margin. Fluids are released from minerals as the slab sinks and heats. The overriding crust may shorten, uplift, fracture, and deform over very long periods. Seen from above, this arrangement can form a graceful arc of islands or a rugged coastal mountain chain. Seen in terms of mechanics, it is a long contact zone where enormous areas of rock remain in frictional interaction. This regional setting matters because a rare earthquake often occurs on only one part of that wider interface. The whole plate boundary may extend across a very large distance, yet the unusual motion is usually confined to a specific segment, depth range, or structural environment. One part of the boundary may remain locked, resisting motion while stress accumulates. Another part may slip more steadily. Another may host episodic slow movement. To understand the rare event, scientists first locate it within the full boundary system. They ask what plates are involved, how fast they converge, what the geometry of the margin looks like, and how the observed deformation fits into the larger tectonic pattern. The regional setting also includes the shape of the seafloor and the structure of the overriding plate. Offshore trenches mark where the descending plate begins its deep path. Landward of the trench lies the forearc, the outer part of the overriding plate between trench and volcanic arc. The forearc can include an accretionary wedge, a mass of scraped and deformed sediments, as well as basins, ridges, and fractured crust. Farther inland, volcanic systems and uplifted ranges may reflect deeper consequences of subduction. A rare earthquake that begins in the shallow forearc has a different meaning from one centered farther down the plate boundary. The regional setting helps define those differences before the analysis moves inward to the boundary itself. Not all rare earthquakes belong to subduction zones, but many of the most studied examples do. In some places, similar slow or unusual events appear on major strike-slip faults, where plates slide past one another horizontally. In others, they occur within continental collision zones or in complex transition areas where several fault types interact. Yet even there, the same principle holds. The broad tectonic environment must be understood first. Stress patterns, crustal thickness, heat flow, inherited structures, and the arrangement of major faults all influence where rare motion is possible. The wider region is not background scenery. It is the first layer of explanation. At the regional scale, geological history becomes visible in the landscape. Raised marine terraces may show repeated uplift over long intervals. Thick sedimentary basins may indicate subsidence and loading. Folded strata reveal compression. Linear valleys, scarps, and offset landforms speak of faulting. Volcanic chains point to processes tied to descending slabs and mantle melting. These features do not identify a single modern rare earthquake, but they show that the region has long been shaped by forces that continue in the present. The current event belongs to an active system that has been building its form over immense spans of time. Regional observation also reveals that tectonic margins are not uniform. Convergence rates may vary along strike. Sediment thickness may change from one sector to another. Seamounts riding on the downgoing plate may enter the trench and disturb the plate interface. Oceanic plate age can differ, affecting temperature and mechanical behavior. Fracture zones and ridges inherited from seafloor spreading may reach the subduction zone and alter local geometry. In the overriding plate, crustal blocks may rotate, faults may segment the forearc, and basins may open or close. These differences matter because rare earthquakes often appear where such complexity changes the balance between locking and slipping. A regional setting is also defined by recurrence, the tendency of a system to produce related events through time. Large earthquake histories, tsunami deposits, uplift records, and long monitoring archives can show that some margins experience repeated slow slip or tremor episodes, while others show little evidence of them. This does not mean the behavior is perfectly regular. Observations indicate variation in timing, extent, and intensity. It often remains uncertain why one segment produces frequent slow events and another remains quiet. Even so, the regional record provides context. An unusual earthquake is understood more clearly when placed within decades of instrumental data and centuries or millennia of geological evidence. Within research, maps of the regional setting often become the first common language among different methods. Seismologists study wave patterns, geodesists measure deformation, marine geophysicists image the seafloor and subsurface structure, geologists trace uplift, folding, and sedimentation on land. Petrologists infer thermal and fluid conditions from mineral behavior. Each field sees a different part of the system, but the regional tectonic framework allows their observations to connect. It shows where the plate boundary lies, where the trench and forearc sit, where the arc rises inland, and where unusual motion fits within the wider plate interaction. The scientific alarm associated with a rare earthquake begins to deepen at this scale, because the event is no longer only a local anomaly in the records. It becomes a process occurring within one of Earth's major stress systems. A slow displacement near a subduction margin is not just a technical curiosity. It is motion on a boundary known to produce great earthquakes and major seafloor change. This does not mean that every rare earthquake leads directly to a disaster. Observations do not support such a simple rule. It does mean that the event is interpreted within a setting where the transfer of stress matters, and where the consequences of fault behavior can extend across large regions. So the broader region comes into view as a moving frame. Ocean basin, trench, forearc, coastline, mountains, and inland arc are all parts of one connected tectonic arrangement. The rare earthquake belongs to that arrangement before it belongs to any single fault patch or local measurement. The calm coast and the quiet instruments are now placed inside a continental or oceanic margin, shaped by long convergence. The surface signs and the monitoring network gain meaning because the region beneath them is already known to be under strain. In that broad setting, the uncommon event becomes legible as part of a larger and older motion that has never truly ceased. Within this broad regional setting, the attention settles on the place where the moving plates actually meet. This is the plate boundary in its mechanical sense. Not only a line on a map, but a vast contact surface between masses of rock that are forced together over long periods of time. In a convergent margin, one plate advances and bends downward beneath the other. The upper plate resists, deforms, and adjusts. Between them lies an interface that may extend for hundreds of kilometers from near the trench down into deeper parts of the Earth. It is along this interface that stress builds, holds, and from time to time is released. To understand a rare earthquake, the first inward step is to understand this convergence itself. Convergence is slow in any human measure, yet it is relentless. Each year, one plate may move a few centimeters toward another. The rate differs from one margin to the next, but the meaning remains the same. Rock is carried toward a boundary that cannot simply absorb the motion at the surface. Some part of the movement is taken up by steady deformation. Some part is stored as elastic strain, meaning that the rocks bend and hold energy while resisting slip. Some part may be released in earthquakes. The boundary is therefore not quiet even when no event is being felt. It is always active in a mechanical sense, because the plates never stop pressing together. The descending plate, often an oceanic plate, approaches the trench and bends downward. This bending is itself a sign of the forces involved. The plate is cold and relatively rigid near the surface, but it is not infinitely strong. As it curves into the earth, it fractures, flexes, and changes stress internally. Sediments lying on top of it may be scraped away or dragged downward. At the same time, the overriding plate above the boundary is compressed and warped. The forearc may shorten. Inland regions may rise. Basins may tilt. These broad changes are part of the visible result of plate convergence. But the crucial process lies at the contact where the two plates either stick or slide. For long intervals, parts of the plate boundary remain locked. Locked means that friction and normal pressure prevent the plates from sliding past each other, even though tectonic forces continue to drive them together. The relative motion does not disappear. Instead, it is stored as strain in the surrounding crust. The upper plate may be pulled slowly toward the trench and downward, bending like a broad board under load. The lower plate continues to dive, carrying the imposed motion into deeper levels. This locked condition is central to many major subduction earthquakes, but it is also essential background for rare earthquakes, because unusual slip often occurs beside, above, or below locked regions. Other parts of the interface may not lock in the same way. Some segments may creep, meaning that they slip gradually without generating strong seismic shaking. Others may alternate between periods of sticking and periods of slow movement. The balance depends on pressure, temperature, rock type, fluid conditions, and the roughness of the surfaces in contact. At the scale of the whole plate boundary, convergence is therefore partitioned. One portion stores stress efficiently. Another releases some of it gradually. Another may host repeated slow slip events. When scientists map the system, they are not simply tracing one uniform plane, they are identifying a boundary whose behavior changes from place to place. This changing behavior helps explain why rare earthquakes are both significant and difficult to interpret. If the entire interface behaved in one consistent way, motion would be easier to predict. Instead, convergence creates a mosaic of mechanical conditions. Near the trench, soft sediments and high pore fluid pressures may reduce resistance to sliding in some settings. Farther down, increasing temperature alters minerals and affects frictional behavior. Irregular features on the downgoing plate, such as ridges or seamounts, may increase local locking or disrupt it. Fractures within the upper plate may redistribute stress. The converging system is continuous, but it is not uniform. At the outer scale of process, one of the clearest ideas is the earthquake cycle. This term describes the repeated pattern in which stress accumulates on a fault during a period of relative locking, and is then released partly or suddenly during an earthquake or gradually during other forms of slip, in subduction zones. This cycle can span decades to centuries for great earthquakes, while smaller or slower events may recur more often. A rare earthquake fits within this cycle, though not always in a simple way. It may release part of the accumulated strain. It may alter stress around a locked patch. It may occur repeatedly in one depth range while leaving another unchanged. Observations indicate that slow and unusual slip are part of the full behavior of convergent margins, not separate from it. The geometry of convergence is also important. The downgoing plate does not descend at the same angle everywhere. In some margins, it slopes gently beneath the upper plate for a long distance. In others, it dips more steeply. This affects where different pressure and temperature conditions are reached and where slow or fast slip may be possible. The shape of the coast, the width of the forearc, and the distance between trench and volcanic arc all reflect this geometry in some way. From the standpoint of the rare earthquake, these broad geometrical factors define the physical space in which the event unfolds. Mechanical coupling is another useful term at this level. Coupling refers to how strongly the two plates are linked by friction at a given part of the interface. High coupling suggests that the plates are locked and storing strain. Low coupling suggests that more motion is accommodated by steady or episodic slip. Coupling is not measured directly at depth. It is inferred from surface deformation, seismic behavior, and modeling. Because of this, uncertainty remains. Observations may indicate strong locking offshore in one segment and weaker locking in another. It may remain uncertain exactly how sharp the boundary is between those segments or how coupling changes with time. Even so, the concept helps connect the slow motion seen at the surface with the hidden mechanics of plate convergence below. In a rare earthquake setting, what alarms scientists is often not convergence alone, but a change in how convergence is being accommodated. The plates are always moving toward one another. That part is expected. The concern begins when instruments show that a section of the interface has started to slip in an unusual way, or that tremor and deformation suggest a transfer of strain toward a more strongly locked region. The mechanical frame of convergence makes such observations meaningful. Without it, the event would be only a local disturbance. Within it, the event becomes part of the larger distribution of stress across one of the most powerful fault systems on the planet. The surface above may still appear calm, yet at depth, the plates continue their long contact. One descends, one resists. Between them, the interface records the struggle between motion imposed by tectonics and resistance imposed by friction and rock strength. Rare earthquakes arise within this struggle. They do not replace the larger process. They express one form of it. In the converging margin, every quiet year is still a year of pressure, bending, and stored strain. The unusual event simply reveals that the boundary is adjusting in a manner that departs from the ordinary expectation of silence followed by sudden rupture. So the process layer becomes clearer. The regional setting defines where the event belongs. Plate convergence explains why stress is present at all. The interface between the plates is a surface of variable locking, creeping, and intermittent release. The rare earthquake enters this system as a particular mode of accommodation, one that can unfold without the unmistakable violence of a common quake. To scientists, that difference is precisely why it matters. It means the boundary is active in a quiet way, and quiet movement on a major convergent margin can carry consequences far beyond its faint expression. At the upper part of the plate boundary, the motion of convergence enters a shallower and more delicate zone. Here the rocks lie closer to the seafloor and the coast, and the overlying materials include thick accumulations of marine sediment, fractured crust, and layers that have been folded, sheared, and carried forward over long periods of compression. This is the shallow deformation region, where the large movement of plates does not always appear as a single clean break. Instead, it is expressed through bending, squeezing, tilting, and gradual shifting distributed across a broad outer belt of the margin. The rare earthquake begins to take on a more specific setting here, because shallow parts of a boundary often behave differently from the deeper, hotter regions below. The rocks and sediments in this outer zone are commonly weaker and more broken than the deeper crystalline crust inland. Sediments arriving on the descending plate may be scraped off at the trench and added to the front of the overriding plate. Over immense spans of time, this process can build a wedge-shaped mass of deformed sediment and fractured rock. Some layers are folded like compressed fabric. Some are cut by faults that carry slices of material over one another. Some remain rich in water and fine clay minerals. The result is a margin whose upper structure is complex, layered, and mechanically variable. When tectonic stress passes into this setting, the response is often spread out rather than sharply focused. Shallow deformation is important because it changes the way motion at depth reaches the surface. If a section of the plate boundary begins to slip slowly, the land above may not move as a rigid block. Instead, the overlying materials bend and warp. A coastal terrace may rise by a small amount. A basin may tilt. A low plain may settle while a nearby ridge lifts. The pattern may extend across many kilometers, and each local change may seem small on its own. Together, these changes trace the geometry of deformation in the shallow crust. This is why surface displacement from rare earthquakes often appears broad and smooth rather than abrupt. The shallow zone spreads the signal. The sediments in this region play a large role. Sediment is loose material such as mud, sand, silt, and gravel that accumulates in layers over time. In subduction margins, these layers may become compacted, folded, and faulted, yet they can remain mechanically softer than older igneous or metamorphic rocks. Their softness allows strain to be distributed through many small structures. Instead of one dominant fault taking all the movement, numerous faults and folds may each absorb a small share. This distributed deformation makes the outer margin seem quiet even while it is active. It also makes interpretation more difficult, because the surface expression of motion can be subtle and spread over irregular ground. Near the trench and along the lower part of the continental slope, the shallow plate boundary can also be affected by topography carried in on the descending plate. Undersea mountains, ridges, or fracture zones may enter the subduction system and push against the overriding plate. This can locally increase deformation, uplift, and faulting in the outer wedge. In some places, it may strengthen contact between the plates. In others, it may disrupt continuity and create pathways for fluids and fractured zones. At the level of shallow deformation, such features help shape where the ground above lifts, sinks, or strains during unusual slip. The outer belt is therefore not only soft and layered, it is also uneven in structure. One of the quiet characteristics of this shallow region is the way it stores and releases strain without always producing strong shaking. Ordinary earthquakes often involve a rapid rupture that sends out energetic seismic waves. In the shallow deformation zone, however, part of the tectonic motion can appear as gradual folding, aseismic slip, or small repeated adjustments on many minor structures. Aseismic means movement that produces little or no ordinary earthquake radiation. This term is useful here because the outer margin often changes in ways that are real and measurable yet not strongly felt. The rare earthquake belongs naturally to such a setting, where motion may be present without the familiar violence of a common shock. The seafloor above this zone can preserve the evidence in clear forms. Marine surveys often reveal ridges formed by compression, fault scarps that step the seabed, folded sedimentary layers, and basins trapped between growing structures. Some features record long-term tectonic shortening. Others may respond more directly to recent deformation. Repeated mapping can show changes in elevation or subtle offsets, though the deep ocean remains difficult to monitor continuously. On land, uplifted shorelines, altered drainage, and the slow tilting of coastal ground may serve as equivalent surface clues. None of these features is necessarily dramatic in the moment. Their value lies in comparison through time. This part of the boundary is also strongly affected by the weight and properties of overlying sediments. Thick sediment piles can load the shallow wedge and influence how stress is distributed. They can trap fluids within pores and low permeability layers. They can weaken when sheared, especially if clay-rich. They can also conceal faults from direct view, making geophysical imaging essential. The rare earthquake, when it passes through or near this zone, is filtered by these conditions. Its shallow expression becomes a product not only of slip on the plate interface, but also of the materials above that interface and their tendency to bend, compact, and fracture under pressure. In many margins, the shallow region is where the boundary between land and ocean is most dynamic over human timescales. River sediment enters from inland. Storms reshape deltas and beaches. Submarine landslides can occur on steep slopes. Tides, waves, and erosion modify the coastal surface. Because of this active environment, tectonic deformation must be separated from many non-tectonic changes. A sinking marsh may reflect sediment compaction as much as crustal motion. A changing shoreline may reflect storms as much as uplift or subsidence. Scientists therefore look for broad coherence and repeated measurements. When shallow deformation from a rare earthquake is present, it tends to leave a regional pattern rather than a single isolated anomaly. There is also uncertainty in how the shallow plate boundary behaves from place to place. Some observations indicate that the very shallowest part of certain subduction interfaces can slip in tsunami-genic earthquakes, which are earthquakes that produce significant seafloor displacement and can generate tsunami waves. Other observations suggest that in many settings the shallowest zone may deform more gradually or absorb motion through distributed strain. In the context of rare earthquakes, it remains uncertain in some regions how far shallow slow slip extends toward the trench, and how efficiently that motion changes stress in adjacent locked areas. The shallow deformation field records the result, but translating that record into exact fault behavior remains difficult. Still, this zone provides an essential bridge between the deep mechanics of convergence and the visible world at the surface. It is here that the hidden motion of the plate interface is translated into tilted ground, uplifted margins, warped seabeds, and broad patterns of coastal change. The deformation is gentle in rate and wide in extent, yet it is not trivial. It shows that the upper crust is responding to forces below in a coordinated way. In rare earthquakes, such shallow response may be one of the first clear signs that an unusual release of strain is underway, so the inward journey pauses in a band of compressed sediment, fractured crust, and slow surface warping. The shallow deformation region does not announce itself with obvious violence. It moves through subtle uplift, quiet subsidence, gentle tilting, and distributed strain across the outer margin. Here the great force of plate convergence becomes softer in expression, but no less real. The coast, the seafloor, and the upper crust register the change with patience. And in that patient record, the rare earthquake begins to show its outline more clearly. The rare earthquake now comes into focus as motion on the fault itself, not yet in the deeper materials around it, but in the act of slipping. This is the hidden slip that gives the event its unusual character. In an ordinary earthquake, two sides of a fault remain locked until stress overcomes friction, and the fault breaks rapidly. The motion is sudden. It sends strong seismic waves through the crust. It is felt at the surface as shaking that begins and passes in moments or minutes. In a rare earthquake of the slow kind, the fault also moves, and it may move by a meaningful amount, but the movement is spread across much more time. The fault does not snap in one violent release. It glides, pauses, and continues in a manner that can last for days or longer, quietly redistributing strain without the same sharp seismic signature. Slip is the relative movement of one side of a fault past the other. In both ordinary and rare earthquakes, slip is the central process. The difference lies in rate, duration, and the way energy leaves the fault. When slip is rapid, the surrounding rock is shaken strongly, and the event becomes a familiar earthquake. When slip is slow, much less energy is radiated as ordinary seismic waves, even if the total displacement is large enough to matter tectonically. The motion is still real. The fault still adjusts, stress is still transferred, yet the event remains partly concealed because the usual signal of strong shaking is weak or absent. This slow form of motion is often called slow slip. The term is simple and direct. It refers to fault displacement that occurs too gradually to produce the abrupt shaking of a typical earthquake, but too distinctly to be treated as ordinary background creep. It is a measurable release of strain, often occurring over a defined patch of the plate boundary and over a limited span of time. Slow slip may last several days, several weeks, or in some cases even longer. It can recur in some regions with a rough pattern, though not always with strict regularity. In other regions, it may be rare enough that each episode draws close attention. What makes hidden slip important is not only its quietness, but also its ability to alter the mechanical state of nearby parts of the fault. A slow event may release stress in one area while increasing stress in another. It may migrate along the plate boundary. It may occur beside a locked section that is capable of generating a much larger ordinary earthquake. For this reason, scientists do not treat slow slip as harmless simply because it lacks violent shaking. The concern arises from its role in the wider fault system. A quiet event can still be a meaningful tectonic event. The pace of a slow earthquake changes how it is detected. Ordinary earthquakes announce themselves through sharp arrivals of seismic waves. Slow slip is usually recognized through deformation, weak tremor, or both. Ground stations begin to show motion over many days. Offshore pressure records may shift gradually. Faint seismic signals may appear as tremor, a trembling pattern rather than a clear impulsive rupture. In some cases, there is little tremor at all, and the event is known mainly from geodetic measurements. This is one reason the phenomenon remained difficult to identify until instrument networks became dense and precise enough to resolve slow changes in position. The hidden slip itself can take different forms. Some events appear as broad and smooth displacement across a fault patch, with a gradual beginning and end. Others evolve in pulses, where slip accelerates, slows, and then resumes. In some regions, the source seems to migrate along the fault, as if one slipping segment nudges the next into motion. This migration is not like a crack racing at high speed through rock. It is slower, quieter, and more diffuse. The event may unfold over tens or hundreds of kilometers, while remaining almost invisible to anyone above unless instruments are watching carefully. A useful way to think about the difference is to compare the release of strain rather than only the amount of slip. A rare, slow earthquake may involve displacement that, in another context, would be associated with a moderate, ordinary earthquake. But because the displacement is stretched across time, the power of the seismic radiation is much lower. The same fault system therefore has more than one way to move. It can release strain suddenly, or it can release strain gradually. The rare event reveals that the boundary is capable of both modes under different conditions. This quiet release does not mean the fault is sliding freely without resistance. The existence of a defined slow event suggests that friction is still playing an active role. The fault resists motion, then permits it in a sustained but restrained manner. The details depend on local conditions that will become clearer farther inward, including fluid pressure, mineral composition, and temperature. At this stage, it is enough to see that slow slip is neither full locking nor simple continuous creep. It is an intermediate behavior, episodic and distinct, with its own rhythm and consequences. Scientists sound the alarm after such events not because every slow earthquake directly leads to disaster, but because the occurrence of hidden slip can indicate a change in the stress balance of an active plate boundary. Observations indicate that in some regions, slow slip repeats frequently without immediate large earthquakes. In other settings, slow events have appeared before or after larger ruptures. It remains uncertain how universal these relationships are. The Earth does not offer one simple rule that fits every subduction zone or every fault. Yet the evidence is sufficient to show that hidden slip is part of the earthquake system, not an isolated curiosity. The rarity of a given event may come from several sources. It may occur in a region where slow slip has seldom been observed. It may extend farther than usual, last longer than expected, or appear at an unusual depth. It may coincide with tremor patterns or surface deformation that depart from the known background behavior of that margin. When this happens, scientists compare the new event against previous episodes and against fault models. The alarm grows when the pattern suggests that a larger than ordinary volume of strain is being rearranged, especially near a strongly locked segment. The hidden nature of the slip also changes public perception. A strong earthquake enters memory at once. A rare slow one enters mainly through scientific interpretation. Communities may hear that an unusual earthquake is happening, even though they have felt nothing distinct. This can seem contradictory, but it reflects a deeper truth about the Earth. Significant tectonic motion does not always arrive in dramatic form. Sometimes it is spread across days, hidden within broad deformation, and revealed only through patient observation. The fault is moving all the same. In this region of the story, the earthquake is no longer defined by the surface landscape or the observing network alone. It is defined by the fault's manner of motion. Hidden slip is the rare earthquake in its most essential form, displacement without the usual sudden shock, strain release without strong seismic radiation, a real tectonic adjustment unfolding at a pace that the planet allows but human senses often miss. The motion is quiet, yet it is not small in meaning. It changes the state of the boundary. It shows that the fault has entered an active phase of release. And because that release occurs on a major tectonic system, the scientific response becomes one of close and sustained attention. Around the slipping part of the fault lies the surrounding crust, a broad shell of rock that both carries stress and responds to its release. This crust is not uniform. It is built from layers formed in very different ways and at very different times. In the setting of a rare earthquake near a subduction margin, the crust above and around the fault commonly includes marine sediments, altered volcanic rocks, fragments of older oceanic crust, and deeper crystalline rocks that have been fractured and reshaped by long tectonic pressure. The hidden slip does not occur in empty space. It takes place within this varied rocky framework, and the character of that framework influences how stress is stored, how deformation spreads, and how signals reach the surface. At the seafloor and in the shallow outer wedge, sediment often dominates. Mud, silt, sand, and finer clay-rich layers accumulate over long intervals, are carried toward the trench, and then are compressed, folded, and faulted as plate motion continues. These sediments are not merely passive cover. Their thickness, water content, and grain structure affect the mechanical response of the margin. Thick sediment can soften the shallow part of the system and allow deformation to spread across many faults and folds. Thin sediment can leave rougher underlying rock in closer contact across the boundary. Because rare earthquakes often involve slow and distributed motion, the presence or absence of sediment is one of the important conditions that shapes the surrounding crust. Beneath or landward of these sediments lies more consolidated crust, meaning rock that has been buried, compacted, cemented, and transformed into stronger material. In subduction margins, this crust may include basalt from former oceanic settings, volcanic arc rocks formed from ancient eruptions, and metamorphic rocks altered by heat and pressure. Metamorphic means that an older rock changes its minerals and internal structure without fully melting. These stronger rocks can hold stress more efficiently than loose sediment. They may also fracture in more persistent ways, creating networks of cracks and faults that influence how forces move through the margin. A rare earthquake occurring near the boundary between weak sedimentary layers and stronger consolidated crust may therefore produce a distinctive pattern of surface displacement and seismic signals. Fracturing is a central part of this region. The crust around an active plate boundary is crossed by faults, joints, and zones of broken rock created by repeated episodes of tectonic loading and release. Some fractures are large enough to offset whole rock packages. Others are small cracks that mainly serve as pathways for fluids. Together they reduce the crust from a simple solid block to a complex mechanical body, with preferred planes of weakness. When the main plate interface begins to slip slowly, these fractures can absorb secondary deformation, redistribute local stress, and shape the way the overlying crust bends. The hidden slip on the fault is therefore accompanied by a quieter adjustment in the surrounding rocks. One important property of crustal rocks in this context is rigidity, the tendency of a material to resist deformation under stress. A rigid block transfers force differently from a soft or broken one. If the crust above a slipping fault patch is relatively rigid, the deformation at the surface may appear broader and smoother because the block bends over a wider span. If the crust is highly fractured and mechanically weak, strain may localize into smaller structures, producing a more irregular pattern of uplift, subsidence, or horizontal shift. Scientists use these differences to interpret the likely rock conditions around the source of a rare earthquake, though uncertainty often remains because the deep structure cannot be seen directly. Marine geophysical imaging has shown that crust around subduction zones often contains large contrasts over short distances. One ridge of harder rock may sit beside a basin filled with thick sediment. One section of the incoming plate may be smooth and sediment-covered, while another carries rough topography and faulted crust formed long before it reached the trench. These contrasts matter because they change the geometry of contact across the plate boundary. A rough incoming plate can indent and fracture the overriding crust. A smoother one may promote more uniform contact. In the setting of a rare earthquake, the surrounding crust is therefore part of the event's explanation, not simply the medium through which the effects are transmitted. Temperature and pressure also shape the rocks of this region, though at this layer the focus remains on their structural effects rather than deeper mineral changes. As rocks are buried and compressed, pores close, water is expelled or trapped, and strength evolves. Some layers become more compact and resistant. Others remain weak because of fine grain size, clay content, or continuing fluid overpressure. The surrounding crust thus becomes a mixture of stronger and weaker domains, each with its own response to stress. Slow slip on the fault interacts with this mixture. The event may propagate more easily beneath a weak and fractured overlying crust, or it may be partly inhibited where stronger blocks clamp the interface more effectively. These relationships are active subjects of research because they help explain why rare earthquakes are common in some structural settings and less evident in others. The crust around the fault also controls how the event is recorded. Seismic waves traveling through highly fractured material may lose energy more quickly and arrive less clearly at distant stations. Deformation above a weak sedimentary wedge may be spread over such a broad area that the signal is visible mainly through precise geodetic measurements. Ocean bottom instruments placed above rugged basement or thick sediment will record different local responses even if the same slow event is occurring below. In this way, the surrounding crust acts both as a participant in the mechanics and as a filter on the observations. There is evidence from several subduction zones that certain rare earthquakes cluster, where the incoming plate carries features such as seamounts, ridges, or fracture zones into the trench. These features disturb the overlying crust, creating abnormal stress fields and zones of intense breakage. Observations indicate that such heterogeneity can influence both locking and slow slip. It remains uncertain in many individual cases whether a given structural feature promotes rare earthquakes directly or only changes the pattern of deformation after slip begins. Still, the association is important enough that scientists examine crustal structure carefully whenever an unusual event is detected. On land, the influence of the crust appears in the pattern of tilting basins, reactivated upper plate faults, and local uplift or subsidence. A broad rare earthquake may not create new spectacular ruptures at the ground surface, yet it can subtly adjust older structures. Small inland faults may take up part of the strain. Sedimentary basins may subside slightly as neighbouring blocks rise. Rivers may alter gradient by a small amount. These are not separate phenomena from the earthquake. They are the crust's distributed response to a deeper change on the plate boundary. This region also reminds scientists that faults are embedded in real geological material with memory. The crust preserves the effects of earlier earthquakes, earlier fluid movement, earlier burial, and earlier deformation. A slow event does not begin on a blank surface. It enters a rock mass already shaped by long history. Previous fractures may reopen. Old fault zones may guide strain. Buried contrasts in rock type may focus bending. The present motion is therefore conditioned by the inherited structure of the crust, and that inherited structure can make one segment of a tectonic margin behave very differently from the next. So the picture grows more specific. Hidden slip occurs on a fault, but the fault is surrounded by sediments, fractured blocks, compacted layers, and rigid crustal masses that shape every aspect of the event. The surrounding rocks store part of the strain, release part of it, and distribute the rest toward the surface in quiet deformation. Their structure helps determine whether motion remains broad or becomes localized, whether signals are strong or weak, and whether the rare earthquake remains confined or interacts with nearby stressed regions. In this rocky shell around the fault, the uncommon event is given texture, complexity, and consequence. Within the fractured crust around the fault, water becomes one of the quiet but decisive agents in the behavior of a rare earthquake. This water is not present as open underground streams in the ordinary sense. It is held in pores between grains, in cracks between rock fragments, and within minerals themselves. Under pressure, it moves, collects, escapes, and at times becomes trapped. In the fault zone and the rocks around it, this fluid can change the balance between resistance and motion. A rare earthquake is therefore not only a story of rock pushing against rock, it is also a story of pressure within very small spaces, where fluid influences whether a fault remains stuck or begins to slide. In geological language, pore pressure refers to the pressure of fluid within the tiny voids and fractures of a rock. This concept is central here because friction on a fault depends partly on how strongly the two sides are pressed together. If fluid pressure rises within the fault zone, it can reduce the effective force holding the rock surfaces in contact. The total weight of overlying rock remains the same, but the grain-to-grain contact that resists sliding becomes weaker. In simple terms, pressurized fluid can help a fault slip more easily. This does not mean that water alone causes an earthquake. The tectonic stress is still required, but fluid pressure can alter when and how that stress is released. Subduction zones provide many opportunities for fluid to enter and move through the system. Oceanic crust forms at seafloor, spreading centers, and then spends long periods interacting with seawater before it reaches a trench. Water penetrates cracks, alters minerals, and becomes locked into the structure of the crust and upper mantle rocks of the descending plate. As that plate sinks and heats, some minerals become unstable and release water. Sediments carried downward also lose water as they are compacted and heated. These fluids then move into surrounding fractures and porous layers. The fault zone becomes part of a larger fluid system, fed by both the descending plate and the deformed material above it. The pathways for movement are uneven. Some parts of the crust are highly fractured and permeable, meaning that fluid can pass through them relatively easily. Other layers are fine-grained and seal-like, trapping fluid beneath them. Permeability is the ability of a material to allow fluid to move through connected pores or fractures. In the setting of a rare earthquake, high permeability may permit pressure to dissipate, reducing the tendency toward sudden failure. Low permeability may trap fluid and allow pressure to rise, weakening the fault locally. The fault zone is therefore not only a mechanical boundary, but also a hydraulic one, shaped by the movement and confinement of water at depth. In the shallow and middle parts of subduction margins, clay-rich sediments often play a major role. Clays are fine-grained minerals that can hold water and deform in a smooth, distributed way under stress. Some clay-rich layers are weak even under ordinary conditions. When fluid pressure rises within them, their resistance to shear can decrease further. Shear is the force that causes one part of a material to slide past another. A fault zone rich in such minerals and under high fluid pressure may favor slow, stable, or episodic slip rather than a single abrupt rupture. This connection helps explain why rare earthquakes are often associated with parts of plate boundaries where sediments and fluids are abundant. Observations from boreholes, laboratory studies, and geophysical imaging support the importance of fluids, though the exact conditions at depth are difficult to measure directly. Rocks retrieved from ancient fault zones often show evidence of fluid circulation, mineral precipitation, and repeated sealing and reopening of fractures. Modern seismic and electrical studies can sometimes detect zones that appear fluid-rich because they conduct electricity differently or alter wave speeds in characteristic ways. These observations indicate that fluids are widespread in active margins. It often remains uncertain, however, how pressure changes in real time during a particular rare earthquake, because the critical zones lie deep below the surface and offshore in many cases. The presence of fluids also helps explain why some fault patches can move quietly. When effective pressure is reduced, a fault may slip under lower shear stress than would otherwise be needed. If the surrounding conditions favor restraint rather than runaway rupture, the movement may unfold as slow slip. The fault begins to move, pressure changes, stress redistributes, and the event continues in a controlled but still tectonically important way. In some models, fluid overpressure helps create the transitional behavior between full locking and rapid earthquake rupture. In others, it supports patches of weakness embedded within stronger regions. Either way, fluids are part of the reason the fault can release strain without producing strong ordinary shaking. Fluids also affect the surrounding crust beyond the fault itself. Pressurized water can migrate into fractures and reduce strength in adjacent rocks. It can promote chemical reactions that alter minerals and gradually change the mechanical properties of the fault zone. It can help create clay minerals from older rock, increasing weakness over time. These are slow geological processes, but they matter because the present behavior of the fault reflects its long preparation. A rare earthquake may occur over days or weeks, but the conditions that permit it may have been developing for thousands or millions of years through repeated fluid movement and mineral change. Tremor, the weak and prolonged seismic signal often associated with slow slip, may also be linked to fluids. In several tectonic settings, tremor is observed where fluid-rich conditions are inferred. One interpretation is that small-scale slip and fluid movement within a complex fault zone generate these low, extended vibrations. Another is that fluids help maintain conditions under which many tiny failures occur in sequence rather than one large abrupt break. Observations indicate a strong association in some regions, though it remains uncertain whether fluids directly generate tremor or mainly create the environment in which tremor becomes likely. Even in uncertainty, the connection between water, pressure, and weak seismic activity remains a consistent theme. The scientific alarm around a rare earthquake grows sharper when fluid-rich conditions are thought to border more strongly locked sections of a fault. A fluid-weakened patch may slip slowly and transfer stress toward a neighboring region that remains tight and resistant. In this way, the quiet movement of one zone can matter for the future of another. The fluid itself does not carry the danger. The danger lies in the way fluid pressure influences the distribution of resistance and motion along the fault system. Understanding that distribution is one of the major goals of modern earthquake research. Fluid conditions also vary with depth, temperature, and rock type. Near the surface, fluids may escape more easily through permeable fractures and sediments. At greater depths, compaction and mineral reactions can release additional water, while permeability may decrease in certain layers. allowing pressures to build. These variations create a patchwork of hydraulic conditions along the plate boundary. Rare earthquakes are often thought to occupy particular parts of this patchwork, where the balance between stress, friction, and fluid pressure favors episodic slow slip. This does not produce a simple universal map. Different margins show different combinations of sediment supply, structure, and fluid pathways. Yet the role of fluids appears again and again across the best-studied examples. So this inward layer reveals a fault zone that is not dry, empty, or inert. It is threaded with water under pressure, moving through pores, cracks, and altered minerals. That water reduces effective clamping, modifies friction, weakens clay-rich layers, and helps shape the conditions for hidden slip. The rare earthquake remains a tectonic event driven by plate motion, but its quiet manner depends in part on these unseen fluids inside the fault system. Pressure in tiny spaces changes the fate of enormous masses of rock. Through that quiet influence, water becomes one of the most important invisible participants in the earthquake's uncommon motion. Within the fault zone, where rock surfaces meet under pressure and fluid moves through narrow spaces, the question becomes one of resistance. Why does one part of the boundary remain stuck while another part slips slowly? Why does one event race as a destructive rupture while another unfolds with a little ordinary shaking? The answer begins with friction and strength. Friction is the force that resists sliding when two surfaces press against each other. Strength is the capacity of the fault and surrounding rocks to withstand stress without failing. In a rare earthquake, these properties do not vanish. They govern the unusual motion. The fault slips slowly because its frictional behavior allows movement under certain conditions without developing into a rapid seismic break. Friction in rocks is more complex than the rubbing of smooth solid objects at the surface of daily life. Natural fault surfaces are rough, layered, broken, and chemically active. They contain grains of different sizes, clay-rich seams, fragments of harder minerals, and zones that have been crushed into fine material through repeated movement. Under high pressure, only some parts of the opposing surfaces may carry most of the load. These local contact points matter greatly. If they grip strongly, the fault tends to lock. If they weaken under changing conditions, slip can begin. The whole fault therefore behaves according to countless small contacts spread across a broad, irregular surface. One important distinction in fault behavior is between stable sliding and unstable sliding. Stable sliding means that if motion begins, the fault tends to continue in a controlled way without accelerating into a violent rupture. Unstable sliding means that once slip starts, resistance drops in a way that allows rapid acceleration and ordinary earthquake failure. Rare earthquakes often occur in regions where the frictional properties favor this more stable or conditionally stable behavior. The fault can move, but the movement remains restrained. It does not run away into the abrupt release that defines a common quake. Laboratory studies of rock friction help explain this difference. When geologists shear rock samples under controlled conditions, they find that some materials become weaker as sliding speed increases, while others become stronger or remain relatively steady. A fault that weakens strongly with increasing slip rate is more likely to fail suddenly. A fault that resists or stabilizes as slip begins is more likely to creep or slip slowly. Natural faults are far more complex than laboratory samples, but the same broad principle applies. The way friction changes during motion helps decide whether the event stays quiet or becomes violent. Mineral composition is especially important here. Clay-rich materials often have lower frictional strength than many harder crystalline rocks. Some clays also encourage smooth, distributed deformation rather than abrupt stick-slip failure. Stick-slip is the repeated pattern in which a surface sticks because of friction, then suddenly slips when the resisting force is overcome. This pattern is a useful small-scale analogue for ordinary earthquakes. In contrast, a clay-rich fault zone with abundant fluids may favour more continuous or episodic slow movement. Not all clays behave identically, and not all slow earthquakes occur in the same mineral setting. But the presence of weak minerals is a recurring feature in many studies of slow-slip environments. Other minerals can strengthen or roughen the fault. Quartz-rich and feldspar-rich rocks, common in many crustal settings, may support stronger local contacts and sharper frictional transitions. Basaltic materials from oceanic crust can behave differently again, especially when altered by fluids and temperature. As minerals break down, react with water, or are transformed during burial, the frictional character of the fault may change over time. This is one reason the same plate boundary can host different styles of behavior at different depths or in different segments. Friction is not a fixed number across the entire system. It is a changing property shaped by the rocks present and the conditions they experience. Temperature also influences strength. As depth increases, temperature rises, and the mechanical behavior of rocks changes. At lower temperatures, rocks tend to fracture more readily and support stick-slip behavior. At higher temperatures, they may deform more gradually and plastically, meaning that they bend or flow over time instead of breaking suddenly. Slow earthquakes often occur in the transitional zone between these two broad regimes, where frictional sliding remains possible but the conditions begin to favour slower, more distributed motion. This transition is not a sharp line. It varies with rock type, fluid content, and strain rate. Even so, temperature helps define the depth range in which rare earthquakes are most likely to develop. Fault strength also depends on the history of previous motion. A surface that has slipped many times may become polished in places, rough in others, and packed with extremely fine crushed material called gouge. Gouge can be weak, especially when it contains clay and trapped fluids. Repeated motion can also align mineral grains, create slip surfaces within the broader fault zone, and establish preferred pathways for future movement. In this way, the fault develops a memory. Its present strength reflects not only current pressure and composition, but also many earlier events that have altered its internal structure. This region of the system is therefore neither uniformly strong nor uniformly weak. It is patchy. Small, stronger areas may remain locked while neighbouring weaker areas slip. These stronger areas are sometimes called asperities, meaning zones of greater contact strength or roughness on a fault. In ordinary earthquake studies, asperities are often associated with places that store stress and rupture forcefully. In the context of rare earthquakes, the arrangement of stronger and weaker patches can help explain why slip spreads in a controlled fashion. Weak areas may begin to move first, while stronger patches slow or redirect the process. The fault becomes a mosaic rather than a single plane with one behavior. Observations from natural slow earthquake regions support this patchwork view. Surface deformation patterns, tremor distributions, and modelling of fault slip indicate that rare events often occupy sections of the interface that are neither fully locked nor fully creeping all the time. They appear to exist in a middle state, where the frictional balance allows episodic release. It remains uncertain in many cases exactly how much of this behaviour is controlled by mineral composition, how much by fluid pressure, and how much by the rough geometry of the fault. The likely answer is that all three matter together. Friction and strength are not isolated properties. They emerge from the combined effects of surface roughness, mineralogy, fluids, temperature, and stress history. This is why scientific alarm after a rare earthquake does not come from motion alone. It comes from what the motion reveals about the fault's internal condition. A slow, slip event shows that the boundary has entered a state where resistance has been overcome, but only in a restrained manner. That suggests a particular balance of strength across the system. If that balance changes further, neighbouring sections may behave differently. A weak slipping patch beside a strong locked one is not an abstract model. It is a real configuration that can affect how strain is shared along the plate boundary. So this inner layer brings the focus to the physical resistance of the fault itself. Friction resists motion. Strength determines how much stress the rocks can bear. Weak minerals, pressured fluids, rising temperature, and fault history all influence these properties. In rare earthquakes, the fault does not simply break or remain still. It occupies an intermediate mechanical state where motion is possible without rapid failure. That state is delicate, variable, and scientifically important. It is the reason hidden slip can continue for days or weeks, and the reason such quiet movement may still matter greatly within a larger and more dangerous tectonic system. Once the fault begins to move, the rare earthquake is shaped not only by the materials and pressures around it, but by the way motion travels along the slipping surface. This is the behaviour of the rupture, though in a slow earthquake the word rupture must be understood in a broader and quieter sense than in a common seismic event. In an ordinary earthquake, rupture usually means a rapidly expanding break that moves across a fault at high speed, releasing stored strain in seconds to minutes. In a rare, slow earthquake, the same fundamental process of fault slip occurs, but the spread of motion is far more gradual. The event unfolds as a migrating zone of displacement, sometimes smooth, sometimes pulsed, sometimes irregular, but generally much slower than the violent advance of a typical earthquake rupture. This movement along the fault can be imagined as a front of slipping rock that travels through a boundary already close to failure in some places and more resistant in others. The front does not usually cross the fault all at once. Instead, one patch begins to slip. Then nearby patches follow as local stress changes. The process may continue steadily or in fits and starts. The result is a migrating earthquake, one in which the source area changes position over time rather than releasing all of its strain from one fixed centre. This migration is one of the defining features of many rare earthquakes, and one of the main reasons scientists study them so carefully. It reveals that a fault is not simply either broken or unbroken. It can enter a moving state that passes through the boundary, like a quiet wave of adjustment. The speed of this migration is much lower than the speed of seismic rupture in ordinary earthquakes. A common earthquake rupture may move through rock at a large fraction of seismic wave speed. A slow earthquake migrates many orders of magnitude more slowly, often measured in kilometers per day rather than kilometers per second. This enormous difference in rate is one reason the event produces limited high-frequency shaking. The fault has time to adjust locally as slip spreads, and the release of elastic energy is stretched across much longer intervals. The motion is still tectonic, still significant, and still capable of changing stress, but its rhythm is entirely different. In some events, rupture behaviour appears smooth at first sight. Surface measurements and models suggest a broad patch of slip, expanding or drifting in one direction with relative continuity. Yet closer study often reveals pulses within that broader migration. Slip may accelerate in one small segment, slow, and then pick up again farther along. Tremor may cluster in bursts. Deformation rates may vary from day to day. These pulses suggest that the slipping front is interacting with local differences in friction, fluid pressure, and structure. The fault is not a simple uniform sheet. As slow rupture moves, it encounters patches of varying strength, and the movement adapts to those contrasts. This pulsed behavior is especially important because it shows that slow earthquakes are not merely ordinary creep observed on a larger scale. Creep is continuous or near-continuous fault motion, without clear episodic release. A rare slow earthquake, by contrast, is an event. It has a beginning, a period of active propagation, and an end. Even when the slip is gradual, it is still organized in time and space. The rupture behavior marks this organization. It distinguishes a tectonic episode from the quieter background motion of a boundary that may be creeping steadily all year. The event has a traveling character. It progresses. Some rare earthquakes move predominantly along the strike of a fault, meaning parallel to the long direction of the boundary. Others spread both along strike and down dip or up dip, meaning towards shallower or deeper parts of the plate interface. The direction matters because it determines which neighboring regions are affected by changing stress. A slow event migrating toward a locked patch may increase scientific concern more than one moving away from it, though the exact consequences depend on local geometry and stress conditions. Observations indicate that in some subduction zones, slow slip tends to recur in similar corridors, suggesting preferred routes of propagation. It remains uncertain, however, why some events halt at the same apparent boundaries while others extend farther than expected. The boundaries that limit rupture are a major topic of study. A slow earthquake often does not run freely across the whole fault system. It stops. It may stop because it reaches a stronger patch, a region with different temperature, a change in fluid conditions, or a structural barrier such as a ridge or fracture zone on the descending plate. It may also stop because the available excess stress has been exhausted and the driving conditions weaken as the event grows. In some cases, a later event resumes motion beyond the previous stopping point. In other cases, this same limit persists through many cycles. These patterns suggest that rupture behavior is strongly controlled by the internal segmentation of the fault. Segmentation means that a fault is divided into sections that behave differently from one another. The divisions may not be visible at the surface, yet they can be inferred from repeated earthquake behavior, geological structure, and geodetic models. A slow rupture moving through one segment may transfer stress to the next without immediately crossing into it. That transfer can matter greatly, even if the rare earthquake stays within its own segment. The edge of its rupture is a place where forces change sharply. Scientists pay close attention to those edges because they may help explain later activity nearby. The slow spread of rupture can also illuminate the mechanical state of the fault in a way ordinary earthquakes sometimes cannot. Because the event unfolds over days or weeks, there is time to watch it evolve. Daily or even more frequent position data can show where the slip front seems to be moving. Tremor can map out clusters of activity that accompany the migration. Offshore pressure changes may give further clues. In effect, the fault exposes part of its internal organization while the event is still underway. This real-time view is one reason rare earthquakes are so valuable scientifically. They allow researchers to observe a fault adjusting gradually, rather than reconstructing everything after a sudden shock has already passed. At the same time, interpretation remains difficult. Surface measurements do not reveal the fault directly. They must be translated into subsurface slip-through models, and more than one model may fit the data reasonably well. Tremor may trace some parts of the moving rupture, but not all. Offshore observations remain sparse in many regions. As a result, the exact shape of a slow rupture front and the exact pattern of pulsed slip often remain partly uncertain. Scientists can identify the event, estimate its extent, and infer its general movement, but many fine details remain hidden. This uncertainty does not weaken the significance of the event. It simply reflects the challenge of watching a deep process through limited windows at the surface. Rupture behavior is also one of the clearest links between slow earthquakes and hazard. A migrating slow event can load or unload neighboring fault patches as it passes. The pattern of loading depends on how much slip occurs, where it occurs, and how the rupture front moves through the interface. A quiet event that propagates toward a strongly locked region may alter stress in a way that draws close attention from scientists, even when no damaging shaking accompanies it. Alarm in this context is therefore tied to the path of the rupture as much as to its size. The question is not only how much the fault moves, but where the movement goes. So this deeper process layer reveals the rare earthquake as a travelling release rather than a single instant of failure. The fault begins to slip in one place, then the motion migrates through neighbouring patches, slowed and shaped by barriers, weak zones, and changing conditions along the interface. The rupture may be smooth or pulsed, limited or extensive, orderly or irregular, but it remains a coherent tectonic event unfolding in time. In this moving pattern, the rare earthquake becomes more than hidden slip. It becomes a dynamic rearrangement of stress across a living fault surface, quiet in sound yet active in consequence. As the slow rupture moves along the fault, it leaves behind a pattern of signals that is quieter than ordinary earthquake shaking but still rich with information. These signals travel through the crust and are gathered by listening networks on land and beneath the sea. They do not usually arrive as one sharp burst. Instead, they often appear as weak vibrations, intermittent tremor, and subtle changes in the background field of seismic noise. This is the acoustic face of the rare earthquake. Though acoustic here means only that motion in the earth produces waves that can be recorded. The event remains mostly hidden from daily experience, yet in the instruments it acquires a faint and complex voice. In a common earthquake, the seismic record is dominated by clear wave arrivals. First come the faster compressional waves, which move by squeezing and expanding the rock in the direction of travel. Then come the slower shear waves, which move the ground sideways relative to the direction of travel. After these arrivals, additional waves reflect, scatter, and reverberate through the crust. The sharp onset of these phases allows scientists to locate the source and estimate its size. In a rare, slow earthquake, the fault often slips too gradually to produce the same strong, high-frequency radiation. The energy is released over a longer interval, and much of the record lacks the sudden, impulsive character of an ordinary quake. Instead, one of the most revealing signals can be tremor. Tremor is a weak, sustained, and often irregular seismic vibration that persists longer than a typical earthquake signal and does not break neatly into distinct wave phases. It can continue for minutes, hours, or even longer in episodes that cluster during slow slip. On a seismogram, it may resemble a soft, restless band of motion rather than a single sharp event. Tremor is especially important because it often appears in the same general regions as slow earthquakes and sometimes migrates in step with the advancing slip. It provides a partial way to track the hidden movement of the fault. The origin of tremor is still studied closely. Observations indicate that it is linked to fault motion in zones where fluids, complex fractures, and transitional frictional behavior are present. One interpretation is that tremor arises from many small failures occurring close together in time and space within a broader zone of slow slip. Another is that tiny seismic events and fluid-related processes contribute together to the prolonged signal. It remains uncertain exactly how much of the tremor comes from discrete microfailures and how much from more distributed fault zone processes. What is clear is that tremor is not ordinary background noise. It tends to organize itself in relation to slow tectonic motion. The distinction between tremor and ordinary earthquakes matters greatly. Small normal earthquakes also occur near active plate boundaries, and they may accompany or follow slow slip. But their waveforms are more impulsive and easier to locate individually. Tremor, by contrast, is often emergent, meaning it begins gradually rather than abruptly. Its energy is commonly concentrated in lower frequencies than the sharp cracking signals of brittle failure. Because of this, scientists must use filtering, correlation, and array methods to identify it reliably. A single station may hear only a vague rumble. A network can reveal that the rumble is coherent across many stations and tied to a specific part of the fault. Low-frequency earthquakes form another related part of this signal world. These are small seismic events whose energy is weighted toward lower frequencies than typical earthquakes. In some regions, they appear embedded within tremor and may represent individual brittle failures within a broader slow-slip environment. Their study helps bridge the gap between continuous tremor and discrete earthquakes. The rare earthquake system therefore contains a whole spectrum of motion, from very gradual fault displacement to tiny seismic failures and weak prolonged vibration. The event is not silent. It simply speaks in forms that standard earthquake expectations do not always anticipate. Seismic waves generated during a rare earthquake also travel through crust that is itself complex and layered. Fractured rock scatters energy. Sediment absorbs and softens certain frequencies. Fluid-rich zones can alter wave speeds and attenuation, which is the gradual loss of wave energy with distance. These effects matter because they can blur the already weak signal of tremor and low-frequency activity. A faint event recorded through a thick sedimentary basin may look different from the same event recorded on hard bedrock. Scientists must therefore separate source behavior from path effects, meaning the influence of the rocks the waves travel through. This requires comparison among many stations and careful modeling of the regional structure. The timing of tremor relative to slow slip is one of the most important clues in active monitoring. In some events, tremor appears as the geodetic signal of slip begins to grow. In others, tremor pulses mark the migration of the slow rupture front along the fault. Clusters of tremor may light up one segment after another, almost like lanterns revealing the path of motion in the dark. This imagery is useful only because it clarifies the science. The fault remains hidden. But tremor gives indirect signs of where the state of stress and friction is changing most actively. That is why scientists follow tremor maps closely during unusual events. Not every slow earthquake produces strong tremor, and not every tremor episode is tied to a large geodetically resolved slow slip event. This is one of the important uncertainties in the field. Observations from different margins show different balances between deformation and seismic expression. Some slow events are marked clearly by both ground movement and tremor. Others are seen mainly in geodetic records. Some tremor-rich zones show repeating activity without large accompanying surface displacement. These differences likely reflect variations in fault conditions, including fluid pressure, temperature, rock type, and local stress state. The relationship is strong enough to be scientifically useful, but it is not identical everywhere. Scientists also examine background seismicity during rare earthquakes. Background seismicity means the ordinary pattern of small earthquakes that occurs in an active region even when no major event is underway. During slow slip, this pattern may change. Small earthquakes may cluster differently. The rate of seismicity may rise or fall in adjacent zones. These changes can provide evidence that stress is being transferred, yet background seismicity is naturally variable, and short-term changes are not always easy to interpret. A temporary increase in local earthquakes may be related to the slow event, or it may reflect the normal restless state of the boundary. Caution is therefore essential. Wave analysis during these events often relies on stacking and correlation techniques. Stacking means combining many weak records to strengthen the coherent signal they share. Correlation means comparing waveforms to detect repeated or related patterns. These methods allow scientists to locate tremor more precisely, identify low-frequency events, and track migration across time. The work is patient and detailed. It turns faint vibrations into usable maps of hidden motion. Without such methods, much of the seismic expression of a rare earthquake would remain buried within noise from weather, ocean waves, and the countless small motions of the Earth. The alarm associated with these signals comes from what they imply about fault activity. A strong ordinary earthquake announces itself directly. Tremor and weak waves require interpretation, but once interpreted they can reveal that the fault is active over a broad area even in the absence of damaging shaking. If tremor begins to migrate toward a locked segment, attention intensifies. If low-frequency activity grows in a region with known strain accumulation, scientists become more alert. The signals themselves are quiet, but their meaning can be large because they reveal stress change in real time. So the rare earthquake becomes audible in a restrained and fragmented way. It does not usually crash through the listening network with a single violent pulse. It murmurs through tremor, low-frequency events, weak seismic waves, and subtle changes in the pattern of ordinary background activity. These signals are faint, but they are not vague when viewed together. They trace the hidden work of the fault as slow slip advances through the boundary, in that quiet wave field. The uncommon earthquake leaves a record of motion that careful instruments can hear long before the surface world understands the depth of what is taking place. As the rare earthquake progresses, the main scientific concern begins to shift from the slip itself to the way that slip changes the balance of forces around it. A fault is not an isolated surface. It exists within a connected system of stressed rock, and when one part moves, neighboring parts are affected. This process is called stress transfer. Stress is the internal force per unit area carried within a material. In tectonic settings, it builds slowly as plates move and faults resist motion. When slow slip occurs, part of that stored force is released locally, but it is not simply erased, it is redistributed. Some nearby areas may become less loaded, others may receive an increase in stress. The rare earthquake therefore matters not only for where it slips, but for where its influence spreads. Stress transfer is one of the reasons scientists sound the alarm after an unusual event, especially near major plate boundaries. The slow earthquake may unfold quietly, with little ordinary shaking, yet it can still alter the conditions on a neighbouring, locked section of the fault. A locked section is a region where friction keeps the two sides from sliding, even though tectonic forces continue to push them toward failure. If a slow event changes the stress on such a region, it may bring that section slightly closer to rupture or, in some cases, slightly farther from it. The change is often small compared with the total stress already present, but faults close to failure can be sensitive to even modest adjustments. The idea is simple in outline and difficult in detail. When a portion of the fault slips, the surrounding crust deforms elastically, meaning it bends and stores or releases strain without permanently breaking in the moment. This elastic response transmits force through the surrounding rock. Areas immediately around the slipping patch may feel a reduction in stress because some of the accumulated strain has been released there. At the edges of the slipping zone, however, the effect can be the opposite. Those margins may experience an increase in stress as the moving patch pushes, pulls, or shears against areas that remain stuck. In this way, a rare earthquake can create a pattern of unloading and loading at the same time. This edge effect is especially important near segmented plate boundaries. A slow slip event may remain within one segment, yet its advancing edge can load the neighboring segment without crossing into it. The result is a system in which quiet motion in one area influences the readiness of another area to move. If the neighboring region is weak and already prone to slow slip, the event may encourage further quiet migration. If the neighboring region is strongly locked, the transferred stress may be more concerning. Scientists therefore pay careful attention not only to where the event happens, but to what lies beside it. The same amount of slip can have very different implications depending on the stress state of adjacent patches. Stress transfer can also act vertically along the plate boundary. A slow event in a deeper transitional zone may change stress on shallower locked parts of the fault. Likewise, shallow slip may influence deeper sections where tremor and low-frequency activity occur. The geometry matters greatly. A change that seems small at the source can be concentrated or diluted according to the shape of the fault, the distribution of rigidity in the surrounding crust, and the exact location of locked and weak zones. Because subduction interfaces dip into the earth rather than lying flat, the path of transferred stress is often complex. Models help estimate these effects, but the models depend on assumptions about fault shape, material properties, and the slip distribution itself. One reason this subject receives so much attention is that observations from several regions suggest that slow slip can precede or follow larger ordinary earthquakes, though not in a simple or universal way. In some cases, slow events appear to load neighboring asperities, the stronger patches that tend to store stress more efficiently. In other cases, slow slip may relax part of the stress that would otherwise contribute to a larger rupture. There are also many cases in which repeated slow earthquakes occur without any immediate major earthquake nearby. This mixed record is important. Observations indicate that stress transfer from rare earthquakes is real and significant, but it remains uncertain exactly when that transfer raises hazard substantially, and when it mainly reflects the ordinary breathing of an active fault system. Small earthquakes often respond to transferred stress before large ones do. During or after a rare earthquake, local seismicity may increase in zones expected to receive added stress. These small events can serve as indirect clues to the changing force balance. However, their interpretation requires care. A rise in small earthquakes may reflect a real loading effect, but it may also be shaped by improved detection during the event, temporary fluid movement, or the natural clustering common in tectonically active regions. Scientists therefore look for patterns rather than isolated examples. They compare the spatial distribution of new seismicity with modelled stress changes and with previous episodes from the same region. The timescale of stress transfer also matters. Some changes occur almost immediately as the fault slips and the crust responds elastically. Others unfold over longer periods through viscoelastic relaxation, afterslip, or fluid redistribution. Viscoelastic means a material behaves partly like an elastic solid and partly like a very slow-flowing substance over time. In the deeper earth, especially below the brittle crust, Such behavior can gradually modify how stress is passed through the system after an event. A rare earthquake may therefore have both an immediate influence and a delayed one. The immediate effect may appear in tremor migration or clustered small earthquakes. The delayed effect may alter deformation patterns over weeks or months. Transferred stress does not always increase hazard. In some circumstances, a slow event may reduce stress on a nearby locked patch or release strain from a broader area in a way that temporarily lowers the likelihood of sudden failure in that specific region. This possibility is important because it prevents simple alarmist conclusions. Scientists do not assume that every rare earthquake is a direct precursor to disaster. Instead, they assess the geometry, the slip distribution, the regional history, and the known locked zones of the margin. Concern rises when the pattern suggests loading of a strongly stressed segment, especially one known from geodetic or historical evidence to be accumulating strain over long periods. The difficulty is that the starting stress on a fault cannot be measured directly. Scientists can estimate relative changes in stress from observed slip, but they do not know the exact absolute stress state everywhere along the boundary. A small additional load may matter greatly on a patch already close to failure, or barely at all on a patch farther from rupture. This is one of the deepest uncertainties in earthquake science. The rare event can be measured. The transferred stress can be modelled. But the true readiness of the neighbouring fault to fail remains partly hidden. That uncertainty is one reason the scientific response remains cautious and attentive rather than predictive. The concept of cascading interaction also belongs here. One rare earthquake may trigger another slow event nearby, which then transfers stress onward again. A chain of quiet adjustments can spread through a margin over time, producing a migrating field of deformation and tremor. In some settings, such cascades remain entirely within the world of slow fault motion. In others, they may brush against locked sections that are capable of larger ruptures. The existence of such chains shows that the plate boundary behaves as a connected system. No single event is fully isolated from the surrounding network of strain. So this inner region is defined by force moving beyond the slipping patch. The rare earthquake releases stress where it occurs, but at the same time it shifts that stress through neighbouring crust and along nearby segments of the fault. Some places are eased, some are loaded. Edges become important. Locked zones draw attention. Small earthquakes, tremor, and new deformation may reveal the changing balance. Yet the final meaning remains partly uncertain because the hidden initial state of the fault is never known in full. Stress transfer is therefore both a source of knowledge and a source of caution. It explains why a quiet earthquake can matter far beyond its faint signals, and why scientists respond seriously when a rare event begins to rearrange forces on a major tectonic boundary. From this changing balance of forces, the meaning of the rare earthquake becomes more practical and more difficult at the same time. Scientists now ask what the event implies for hazard, not in the sense of certainty or prediction, but in the sense of measured risk within a known tectonic system. Hazard refers to the potential for a damaging natural event to occur. In earthquake science, that potential depends on many things at once: how much strain is stored, where faults are locked, how stress is transferred, how past events have unfolded, and how the present event compares with earlier behavior. A rare earthquake does not provide a simple answer to any of these questions. It does, however, sharpen them. That is why alarm appears in scientific language after such an event. The alarm is not a claim that disaster is certain. It is a recognition that the conditions of the fault system may have changed in a meaningful way. One of the clearest lessons from modern observations is that rare earthquakes belong to the broader earthquake cycle. They're not separate from the processes that produce damaging quakes. Slow slip, tremor, and ordinary seismic rupture all occur on or near the same major plate boundaries, and they sometimes occur in related places. This connection is important because it means that a quiet event can carry information about parts of the fault that are otherwise hidden. If a slow earthquake occurs repeatedly at the edge of a locked zone, it may help identify the location of that locked zone. If it migrates toward a segment known to have accumulated strain for a long time, concern increases. The event becomes a window into the structure of hazard, even if it doesn't dictate what happens next. At the same time, the evidence does not support a simple rule that rare earthquakes reliably announce a larger rupture. In some tectonic margins, slow slip events occur again and again without any immediate destructive earthquake. They may be a regular part of how strain is managed in the transitional parts of the boundary. In other cases, unusual slow motion has been observed before or after larger earthquakes, suggesting some level of interaction. The problem is that these examples do not form a universal sequence. Observations indicate links, but the links vary in strength and timing from one region to another. It remains uncertain whether a given slow event should be understood mainly as a release of strain, a transfer of strain, or a combination of both with no simple implication for immediate hazard. This uncertainty is one reason earthquake scientists are careful with language. They may state that a rare earthquake has increased attention on a particular margin. They may say that stress changes are consistent with elevated concern in adjacent locked regions. They may intensify monitoring and communication with civil authorities, but they do not usually claim that a larger earthquake is now imminent unless there is much stronger evidence than slow slip alone can provide. The Earth does not offer enough direct access to support such a precise statement. Hazard is not the same as prediction. It is the assessment of possibility in a system known to be dangerous over long timescales. One way rare earthquakes contribute to hazard understanding is through the mapping of coupling. Coupling describes how strongly two sides of a fault are locked together. Regions of high coupling tend to store more strain and are more likely, over time, to participate in larger ruptures. Regions of a lower coupling may host more frequent slow slip or creep. When a rare earthquake occurs, it can illuminate the boundary between these different regimes. If the slow event stops repeatedly at the same edge, that edge may mark a mechanical transition. If tremor clusters below a locked patch, that may help define the down-dip extent of the most hazardous part of the interface. These are indirect clues, but they are valuable because the plate boundary itself cannot be seen directly. The relationship between slow events and tsunami-genic hazard adds another layer of concern in subduction zones. Tsunami-genic refers to fault motion capable of displacing the seafloor enough to generate tsunami waves. Some of the most damaging subduction earthquakes involve substantial shallow slip near the trench. Rare earthquakes are not typically large tsunami-genic ruptures in themselves, especially when they unfold gradually. Yet they can still matter if they reveal that shallow parts of the boundary are active in unusual ways, or if they redistribute stress towards sections where rapid, shallow rupture is possible. The evidence here is especially complex. In some regions, shallow, slow slip appears to occur with little direct tsunami consequence. In others, the behavior of the shallow interface remains poorly constrained because offshore monitoring is limited. It remains uncertain how often rare earthquakes change shallow hazard significantly. But the question is important enough that every well-recorded event receives close study. The historical record also shapes hazard meaning. Some plate boundaries have centuries of written accounts, geological tsunami deposits, uplift records, and instrument data. Others have only a short instrumental history and sparse geological evidence. In a well-documented margin, a rare earthquake can be compared against previous slow events, previous large ruptures, and long-term patterns of strain accumulation. In a poorly documented margin, the same event may be far harder to place in context. Scientists may know that the motion is unusual, yet not know whether it is unprecedented or merely previously unobserved. This difference affects the tone of alarm. Where history is rich, the event can be judged against known behavior. Where history is thin, caution deepens because the full range of possible system responses is less constrained. Another important point is that hazard meaning can differ between scientific and public perspectives. To the public, danger is often associated with felt shaking and visible damage. A rare earthquake may produce little of either. That can make the scientific concern seem abstract. Yet from the scientific perspective, quiet movement on a loaded plate boundary can matter precisely because it alters conditions without releasing energy in the usual dramatic way. The fault may be adjusting in silence. A strongly locked neighbouring segment may remain unchanged at the surface, while its stress state is nudged by the slow event next to it. Hazard, in this sense, is not defined only by what is felt in the moment. It is defined by what is changing in the system that governs future ruptures. Some studies suggest that repeated slow earthquakes may, over long periods, reduce the amount of strain available for larger ruptures in the zones where they occur. This possibility is important because it shows that rare earthquakes are not necessarily harmful in themselves. They may be one way the fault releases stress without generating damaging shaking. However, this apparent benefit does not automatically extend to nearby locked patches. A slow event can relieve one area while increasing concern in another. The spatial pattern matters more than the event label alone. This is why hazard interpretation depends on detailed models of where slip occurred and where the strongest locking remains. Early warning systems and rapid response planning are also influenced by these findings, though indirectly. A slow earthquake generally does not trigger the same immediate public warning that a strong ordinary earthquake does, because it often lacks the abrupt seismic onset needed for automatic alert systems. Instead, its value lies in informing ongoing preparedness. If monitoring indicates unusual slow motion beneath a known hazard zone, agencies may review readiness, increase offshore observations, or update scientific advisories. This response is measured rather than dramatic. It reflects the fact that rare earthquakes change the context of hazard more often than they create an instantly obvious emergency. The central difficulty remains that the fault's future path is not fully knowable. Observations indicate that rare earthquakes can be associated with heightened scientific concern, especially where they load locked regions or depart from known patterns. Observations also indicate that many such events pass without a larger rupture following in the near term. The Earth contains both outcomes. That is why scientists speak of increased probability, changing conditions, or elevated attention rather than certainty. The rare event narrows ignorance in some ways and exposes it more clearly in others. So the meaning of hazard in this setting becomes calm, precise, and unresolved. The rare earthquake matters because it belongs to the same tectonic system that produces destructive earthquakes, and, in some cases, tsunami-generating ruptures. It matters because it can map hidden transitions, transfer stress, and reveal active movement in loaded margins. Yet it does not translate into a simple forecast. It is a signal of significance, not a timetable. The alarm that follows is therefore scientific in the strict sense an alert to change conditions. Grounded in evidence, tempered by uncertainty, and focused on the quiet possibility that a fault system has entered a new and important state. After the meaning of hazard has been weighed, the work turns inward again to the models that scientists use to understand what the rare earthquake is doing below the surface. A model is a structured representation of reality built from observations, physical laws, and simplifying assumptions. In earthquake science, models help translate surface motion, weak seismic signals, and offshore pressure changes into an estimate of slip on a fault at depth. They also help test how stress may have changed, how rupture may have migrated, and how the event fits within the larger tectonic system. Yet every model has limits. It can clarify the hidden process, but it cannot remove all uncertainty, because the fault itself remains buried beneath rock and, in many cases, beneath the sea. One of the most widely used approaches is geodetic inversion. Inversion means working backward from observed effects to infer a hidden cause. Scientists begin with the measured displacement of the ground at the surface. They then calculate what distribution of slip on a buried fault would best reproduce that pattern. If several land stations move seaward and upward by small amounts over a week, a model can estimate where on the plate boundary motion most likely occurred. If satellite radar shows a broad zone of uplift and subsidence, that information can be added. The result is not a direct image of the fault slipping. It is an inferred pattern that best explains the observations within the framework of elastic deformation. This method is powerful, but it depends on assumptions. The fault geometry must be chosen or estimated. Scientists need to know the approximate shape, dip, and extent of the plate boundary. They must decide how finely to divide the fault into patches for calculation. They must also select regularization, which is a mathematical way of preventing the model from becoming unrealistically rough or unstable. Regularization helps when the data are sparse or noisy, but it can also smooth away real complexity. A model that is too smooth may miss sharp changes in slip. A model that is too free may fit noise rather than tectonic motion. The inferred rare earthquake therefore reflects both the data and the modeling choices. Seismic models face similar limits. Tremor locations, low-frequency earthquakes, and weak seismic energy can reveal where activity is concentrated, but they do not map slip directly. Scientists use arrival times, waveform similarity, array methods, and migration patterns to estimate where tremor is occurring and how it moves. These results can then be compared with geodetic models of slow slip. When both approaches point to the same part of the fault, confidence increases. When they differ, interpretation becomes more cautious. It may be that tremor marks only part of the slipping zone, or that the geodetic data are too sparse to resolve the full pattern. The model then becomes a tool not only for explanation, but for identifying what is still unknown. Offshore modeling is even more constrained. Many rare earthquakes occur in subduction margins where the most important slip may lie beneath the ocean. There, land stations see the event only from one side, which reduces geometric resolution. Seafloor pressure sensors and ocean bottom seismometers help greatly, but they are fewer in number and harder to maintain. In some margins, temporary campaigns provide useful snapshots rather than continuous dense coverage. This means that models of shallow offshore slip can carry especially large uncertainty. Observations may indicate that motion has occurred near the trench, yet the exact extent and amount may remain difficult to determine. Because shallow slip can matter for tsunami hazard, these uncertainties are scientifically significant. Physical models go beyond simply fitting observations. They ask why the fault behaves as it does. These models include friction laws, fluid pressure effects, temperature structure, and the mechanical properties of surrounding rock. They attempt to reproduce slow slip behavior by simulating how a fault patch near the boundary between locked and creeping regions responds to stress. Some models generate episodic slow slip naturally when fluid pressure is high and friction has transitional properties. Others require heterogeneity, meaning a patchwork of strong and weak areas. Still others explore how roughness, sediment composition, or structural barriers shape rupture propagation. The value of these models lies in showing which combinations of conditions are capable of producing the kinds of rare earthquakes that are observed in nature. Yet physical models are not unique answers. Different sets of assumptions can sometimes reproduce similar observable behavior. A certain tremor pattern might be explained by one arrangement of fluid-rich weak zones, or by another arrangement with different frictional properties. A broad surface displacement field may fit both a relatively smooth slip patch and a more complex one blurred by sparse observations. This is one of the most important limits in earthquake science. Data constrain possibilities, but they do not always choose a single explanation. Scientists therefore compare many models, test sensitivity to assumptions, and identify which conclusions remain stable across different approaches. Time-dependent modeling adds another layer. Because rare earthquakes unfold over days or weeks, researchers can model how slip evolves rather than only where total slip accumulates. This can reveal whether the event migrates steadily, advances in pulses, pauses at structural barriers, or changes speed as it approaches a locked segment. Such modeling is valuable because it turns the earthquake into a process, not just a final map. However, the need for frequent and precise observations is high. If data are missing for part of the event, the inferred timing may blur. If tremor is intermittent or geodetic solutions are noisy, apparent changes in rupture speed may partly reflect limits in resolution, rather than true fault behavior. Uncertainty enters not only through data scarcity, but also through the Earth itself. Material properties vary in ways that are not fully measurable. Rigidity changes with depth and rock type. Fluid pressure is inferred only indirectly. Temperature structure is estimated from models and regional heat flow rather than seen directly. Fault surfaces may be rougher or smoother than assumed. These unknowns affect how slip at depth translates into deformation at the surface. A model may fit the observed data well while still misplacing the exact slip patch if the assumed crustal properties are wrong. For this reason, scientists describe many results as preferred interpretations rather than absolute maps of reality. Despite these limits, models are indispensable. They show whether the event is likely shallow or deep, compact or broad, isolated or interacting with neighboring segments. They estimate the total moment release, which is a measure of the size of the event based on fault area, slip, and rigidity. In rare earthquakes, moment release can be substantial even when ordinary shaking is weak. Models also allow researchers to calculate probable stress changes on nearby locked zones. Compare the current event to past episodes, and test how unusual the present behavior truly is. Without modeling, the observations would remain a scattered collection of surface changes and faint seismic murmurs. With modeling, they become a coherent scientific picture, even if parts of that picture remain blurred. The limits themselves are scientifically useful. When multiple models fit the observations equally well, that reveals where the monitoring network is still too sparse. When shallow offshore slip remains poorly resolved, it argues for more seafloor instruments. When tremor patterns cannot be matched cleanly with geodetic slip, it points to missing knowledge about the relation between seismic and aseismic motion. In this way, modeling does not only interpret the Earth, It also exposes the edges of present understanding. The rare earthquake becomes both an event to explain and an experiment conducted by nature, showing where scientific tools are strong and where they still need refinement. So this inner layer is one of measured uncertainty. Scientists use inversions, seismic analyses, and physical simulations to reconstruct the hidden slip and understand its mechanics. These models can show much. They can locate likely slip zones, estimate migration, and evaluate stress transfer. But they always rest on assumptions about geometry, materials, and incomplete observations. The rare earthquake can therefore be understood in outline with increasing confidence, while still resisting full description in detail. That resistance is not failure. It is the natural limit of observing a deep, quiet process through indirect signs at the surface. The science advances by working carefully within that limit, refining the picture while admitting where the picture remains incomplete. At the final outward return, the rare earthquake is no longer only a hidden fault process. It becomes a scientific response spread across institutions, instruments, maps, and decisions made in careful language. The alarm that follows such an event does not resemble a siren in the ordinary sense. It is expressed through intensified monitoring, repeated model updates, communication between research groups, and renewed attention to the condition of the surrounding fault system. By this stage, the Earth has already moved. The task is to observe what continues, to assess what has changed, and to place the event within the ongoing duty of preparedness along an active margin. Monitoring is the first and most immediate response. Permanent stations on land continue to track ground position day by day. Seismometers are examined for changes in tremor, low-frequency activity, and small ordinary earthquakes. Offshore pressure sensors and ocean bottom instruments, where available, are checked for signs that the event is still evolving. Satellite radar passes are requested and processed. Each new data point helps answer a simple question that cannot be answered all at once. Is the fault still slipping, or has the main episode ended? Because rare earthquakes can last for many days or weeks, this question matters more here than it does for a typical abrupt quake. The event is not always over when first identified. Scientists also compare the present event against the long background of the region. They ask whether the location matches earlier slow slip episodes, whether the duration is typical, whether the total inferred displacement is larger than expected, and whether the migration path has approached a locked segment more closely than before. These comparisons are essential because a rare earthquake is understood best in relation to its own tectonic setting. A moderate slow-slip event in a margin where such events recur regularly may call for close observation, but not exceptional concern. A larger or less familiar event in a poorly understood segment may justify stronger scientific warning. The alarm is therefore relative, built from contrast between what is normal for a region and what appears unusual. Communication becomes part of the response as soon as those contrasts begin to matter. Research teams exchange preliminary models. Monitoring agencies compare interpretations. Civil protection authorities may be informed that an unusual tectonic event is underway and that attention to related hazards has increased. The language is usually measured. Observations indicate ongoing slow slip. Stress changes may be affecting adjacent regions. It remains uncertain whether the event will influence the likelihood of a larger earthquake in the near term. Such statements are cautious by design. They aim to convey significance without claiming certainty that the science does not possess. Preparedness enters here not as reaction to immediate damage, but as maintenance of readiness in a region already known to be hazardous. Emergency planners may review communication pathways, Tsunami monitoring centers may pay closer attention if the event lies near a subduction margin with shallow locked sections. Infrastructure managers may revisit response procedures for strong earthquakes, even though no destructive shaking has yet occurred. In many cases, daily life continues unchanged on the surface. Yet within the systems responsible for public safety and scientific monitoring, the event creates a period of heightened vigilance. This is one reason the scientific alarm matters. It does not wait for visible disaster before becoming active. The response also includes restraint. Scientists know that false certainty can be harmful. A rare earthquake may raise concern without being followed by a larger rupture. Many slow events end quietly after redistributing some part of the regional strain. If every such event were treated as a direct warning of imminent catastrophe, trust would erode. The proper response is therefore balanced. It takes the event seriously, increases observation, refines hazard assessments, and communicates uncertainty clearly. This balance is one of the mature features of modern earthquake science. It accepts that caution and humility must operate together. Public understanding can be difficult at this stage. The word earthquake often suggests something sudden, felt, and already finished. A rare event of slow slip does not fit that expectation. People may hear that an unusual earthquake is occurring beneath the region even though no strong shaking has been noticed. Scientists must therefore explain that earthquake behavior exists on a spectrum. Some fault motion happens abruptly, some happens gradually. Both belong to the tectonic life of the margin. The present event is unusual not because the plates have begun moving for the first time, but because a particular part of the fault has shifted in a way that deserves close scientific attention. Over time, the event is folded into improved understanding of the margin itself. New data may reveal the location of locked and slipping zones more clearly. Offshore gaps in monitoring may become more evident. Models of coupling, tremor, and rupture migration may be revised. In some cases, the rare earthquake leads directly to better instrument coverage or stronger collaboration between marine and land-based observation programs. Nature provides the event, and science uses it to learn where its current picture is weak. The alarm, therefore, has a constructive side. It is not only a warning, it is also a call to improve the ability to see the next quiet change more clearly. This final region returns attention to the surface world, but not to the surface signs alone. It returns to the human layer of interpretation and readiness. The coast remains where it was, altered perhaps by a slight uplift or subsidence too small for most eyes to detect. The sea continues its ordinary rhythm. Roads, homes, harbours, and cities stand above a plate boundary whose deeper motions remain mostly unseen. Yet after the rare earthquake, that unseen boundary is being watched more closely. The scientific community has recognized that the fault system has adjusted in a significant way. Whether that adjustment proves to be mostly self-contained or part of a broader sequence, it has already changed the state of knowledge. So the alarm after a rare earthquake is best understood as disciplined attention. It is the moment when a quiet tectonic event moves from the hidden interior of Earth into the shared awareness of observers, agencies, and communities responsible for living with long-term geological risk. The event may fade without a larger rupture, or it may become one chapter in a more consequential sequence. Observations can narrow the possibilities, but they cannot eliminate uncertainty. What they can do is justify vigilance, deepen understanding, and keep the connection between science and preparedness active. In that calm and measured response, the final meaning of the rare earthquake becomes clear. It is not only a slip on a fault, it is a reminder that the Earth can change in silence, and that silence itself can be worthy of sustained care. The coast grows quiet again in the scientific record. Lines on maps settle into slower change. Tremor fades or becomes difficult to separate from the ordinary restlessness of the earth. Stations remain fixed in place, still measuring, still listening, while the larger boundary continues its patient motion beneath sea and land. Nothing in the broad landscape reveals the full complexity below. Hills hold their shape. Water moves with the tide. Night comes over harbours, cliffs, wetlands, and distant slopes, and the surface keeps its calm appearance. Beneath that calm, the fault remains part of a living planet. Plates continue to converge. Stress continues to gather and release in forms both sudden and slow. The rare earthquake has shown one of the quieter ways that Earth adjusts itself. It has revealed motion without spectacle, force without noise, and significance without immediate destruction. It has also shown the limits of knowledge, where careful instruments can detect change. Yet the deepest conditions remain partly hidden in rock, pressure, and time. In that measured uncertainty, the work of science continues. Observation becomes its own steady kind of vigilance. Each station, each pressure sensor, each satellite pass adds another small piece to the long record of a moving margin. The record does not end when the event fades. It extends forward through ordinary days, through seasons of weather and changing light, through years in which the ground appears still. The rare earthquake becomes part of that long memory, a quiet entry in the archive of the Earth. So the boundary rests only in appearance. The planet remains active, layered, and slow in its deepest motions. Above it, the world of shorelines, towns, forests, and sea continues in silence, held for a time over forces that do not cease. The night deepens over land and water alike, and the unseen fault carries on beneath them with its ancient, patient work.